Hi, I'm Marc Hinton, and I'll be presenting on behalf of my colleagues at the GSC and the University of Ottawa. We are in year 2 of a 5-year study. I'll provide an overview of our work. We're still in the process of collecting data, but I'll discuss some early results, insights, and our next steps. This study has 3 primary objectives. The first is to better understand and characterize groundwater flow and diffusion in the Champlain Sea Aquitard. The second objective is to investigate the geochemical and physical processes that influence the geotechnical properties and behaviors. Champlain sea muds develop into quick clay, which tend to liquefy and result in failures, from local slumps to large retrogressive landslides. This topic is of interest because of the hazard to public safety and infrastructure. These two issues are related, since the development of sensitivity in these marine sediments generally requires a reduction in the original salinity as a result of groundwater flow and diffusion. The third objective is to establish 2 new reference sites where analyses from multiple disciplines are applied and integrated. The Rideau Valley Conservation Authority, in collaboration with the City of Ottawa, is conducting hazard mapping projects along several creeks in Ottawa. These include consideration of both flood risk and slope stability. One of these projects is along Bilberry Creek, and they engaged a consultant to do geotechnical studies in support of the slope stability assessments. Recognizing the recent work the GSC has done in Champlain Sea sediments, they have supported a parallel study by providing 2 cored boreholes in the fall of 2019. The light blue area on the map shows the marine limit of the Champlain Sea following the retreat of the Laurentide ice sheet. Bilberry Creek is located in Orleans, which is part of suburban Ottawa. The map shows the locations of previous GSC boreholes in Breckenridge, Quebec, and Kinburn, Ontario, which I will refer to in this presentation. The satellite image of Orleans shows the locations of the 2 recent boreholes. BC16 is located along Bilberry Creek, and VC2 is located along West Bilberry Creek, also known as Voyageur Creek. The geotechnical consultant for the Bilberry Creek study planned to drill 16 sites along Bilberry Creek and 2 along Voyageur Creek. The GSC had to consider which sites it wanted to core. Our goal was to identify 2 sites with thickest Champlain Sea sediments, which are more likely to preserve remnant salinity. To that effect, a geophysical survey was conducted to estimate the depth to the underlying till or bedrock by monitoring ambient seismic microtremors for 30 minutes at each of 12 of the planned drill sites. These provided estimates of Champlain Sea sediment thickness shown in this figure, which allowed us to select sites BC16 and VC2. It is a useful, rapid, and inexpensive method. The results are available in an open file report. The goal of the drilling program was to collect continuous, undisturbed core samples throughout the entire thickness of the Champlain Sea sediments. These were collected in thin wall steel Shelby tubes advanced 2 feet at a time ahead of the drill casing. We used both piston and open tube samplers, and occasionally split spoons when the coring failed. In all, 147 Shelby tubes were collected. We experienced some problems with coring, for example, concretions, as you can see with the dented Shelby tube above. The deepest borehole at each site was then cased with PVC to allow for borehole geophysical logging. And we also installed a shallow monitoring well at each site and 4 vibrating wire piezometers in all. We set up a field lab in a rental truck to preserve the cores on site. Cores were sealed in a wax mixture, kept cool, and transported to refrigerated storage at the GSC. The methods are documented in GSC Open File 8723. When drilling was complete, we brought all the core to ENRS in Quebec City to CT scan every core. This is a medical CT scanner that is dedicated to environmental samples such as core. A CT scanner basically provides 3D X-rays of the cores. CT scans are measuring density, which is a very useful property because different grain sizes have different density. In the left image of rhythmites in the base of BC16, We can see very fine details with contrasting low density, darker, fine-grained layers and higher density, brighter, coarse layers. The CT scan allows enhanced interpretation that isn't always obvious to the naked eye. As evident in all three figures, 3D CT scans allows both qualitative and quantitative visualization and analysis. In the lab, we coordinated methods for core extrusions, sample treatments, and rapid analyses of time-sensitive properties. We developed a generalized subsampling plan for the various demands for core. Most subsampling plans were customized according to the CT scan and core logging results. Pore water chemistry is measured on centrifuged pore waters and on cellulosic filter membranes that come to equilibrium with the pore water. The extrusions and analyses remain in progress to respect public health guidelines. One of the first results available was borehole logs of apparent conductivity. This measures the conductivity of both sediment and pore water. In this setting, the apparent conductivity is a reasonable measure of pore water salinity. In this log of BC16, the solid line shows an increasing conductivity with depth to a peak and a rapid decrease near the base of the Champlain Sea, indicated by the dashed line. At BC2, we see a similar pattern with increasing conductivity with depth. We didn't reach the base of the Champlain Sea, but we appear to be near the peak. For comparison, this log is for Breckenridge borehole. It shows a very similar profile shape, again not to the base of the Champlain Sea, but reaching a peak and decreasing. However, the conductivities are higher, indicating more saline pore waters. Now in contrast, Kinburn shows a different pattern. It has high values near the surface, and then they decrease more gently to the base of the Champlain Sea. Now Kinburn is a flowing well with upward groundwater flow. Fresh water in the more permeable sands, gravel, and bedrock are gradually displacing the saline waters upward. However, the conductivity profiles suggest that groundwater flow at BC16, BC2, and Breckenridge are downward, displacing the salt towards the more permeable freshwater zone in the bedrock. Chloride is the dominant anion in pore waters at depth, and it shows a similar pattern as the apparent conductivity. We don't have any results yet from the base of the borehole where we expect the concentrations to decrease again. The chloride and bromide axes are scaled with the chloride-bromide ratio of seawater, so the close correspondence below 5 meters confirmed that the source of salinity is seawater. The chloride results here are plotted again on a different scale. The maximum value is an estimate of glacial seawater chloride, such that the bottom axis indicates the percentage of seawater salinity remaining in the pore waters. In the case of BC16, it's about 15% seawater. For comparison, Breckenridge pore waters peak at 63% seawater. So why the difference? First, let us consider how Breckenridge concentrations got to be the way they are. I presented these results at last year's open house. So if we start with the seawater concentration around 85%, and we recharge fresh waters in at the surface and rapidly flush the bedrock with fresh water, then the marine solutes are gradually displaced downward by groundwater flow and diffusion. At Breckenridge, the measured chloride profile can be effectively simulated using a 1D groundwater transport model. So then, back to our question, what is different at BC16? Why are the concentrations so much lower? One possibility is higher groundwater flow. Another is thinner sediments, which will also decrease the upward diffusion over time. However, there is another possibility, is that groundwater flow could be a little more complex. These figures show borehole geophysical logs in both BC16 and BC2 at the same vertical scale. Magnetic susceptibility logs indicate the presence of magnetic minerals within the sediments. Increases in magnetic susceptibility are generally associated with greater provenance from the Canadian Shield and coarser grain size. We expect these increases near the base of the Champlain Sea sediments, where initial deposition of rhythmites includes coarser, more magnetic sediments. However, in BC16 and BC2, we note examples of minor increases within the middle and upper Champlain Sea sediments. The CT scans show a brighter, more dense horizon approximately 30 centimeters thick corresponding to these increases. If these denser, coarser layers are more permeable and are of sufficient extent to allow lateral groundwater flow, then it could effectively reduce the thickness of the Aquitard. Saline water could flow or diffuse to these more permeable layers and enhance the outflux of marine solutes. At BC16, we've collected a year of hydraulic heads. The upper black line is the shallow monitoring well, effectively the water table. The blue line is the vibrating wire piezometer at a depth of 19 meters. Vertically downward flow is maintained throughout the year. In this figure of hydraulic head versus measurement elevation, it indicates the vertical hydraulic gradients, indicating downward flow at both sites. Now at BC16, we see that the gradient is just over 2%, whereas at VC2, there's a greater gradient of approximately 26% on average, yet it's fairly consistent across the different depths, indicating that the vertical hydraulic conductivity is probably pretty constant. Next, we're looking forward to returning to the labs to complete our initial analyses. We're currently working on a manuscript on the interpretation of stratigraphy and sedimentology based on the CT scans. We'll start considering the various hydrogeological hypotheses for lower concentrations at these sites using groundwater transport modeling. We'd like to consider the results from these boreholes in a wider regional context of the Western Champlain Sea Basin. And we're also exploring additional characterizations to optimize the knowledge gained from these cores. We would like to acknowledge the GSC research programs and the support of our colleagues, both internal and external. Thank you for your attention. If you have any questions, please feel free to contact me.